Hello, welcome to this evening's TI Technology webinar hosted by Texas Instruments. Tonight we'll take a look at engaging your students in STEM activities with TI Technology. I see that many of you are joining us for the first time, so we'd like to offer a special welcome if this is your first T-Cubed Professional Development webinar. We'd also like to thank everyone for completing the live survey on the right side of your screen. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm very happy to introduce our two panelists tonight, Linda Antonone and Cassie Whitecotton. For 28 years, Linda has taught mathematics and science to a diverse population of students at urban schools in both Texas and Ohio. Her passions are helping all students excel and making those connections between mathematics and science using technology. Thanks for being with us, Linda.
Hey, great to be here.
And Cassie teaches physics and AP physics at Pascal High School in Fort Worth ISD. She has 8 years of experience teaching at the high school level, including math, science, and engineering education. Thanks for being with us, Cassie.
Hi, how are you?
Great, thanks, Cassie. We are expecting a large crowd, so your audio is muted. Feel free to send questions to Linda or Cassie using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. Once Linda and Cassie move to the teacher software, that right section of your screen will disappear and it will be replaced with a green floating toolbar at the very top. And you can access the Q&A window by clicking the question icon. This session is being recorded, and as a reminder, we'll provide a link to the event certificate of attendance at the conclusion of the webinar. And once that recording is available, we'd love for you to follow along with your handheld or software, and that way you can download the activities at the conclusion of the webinar and then follow along with the recording once that recording is made available. We don't expect you to have any audio issues tonight, but in the event that you do, try selecting Communicate in the WebEx menu, choose Audio Broadcast, and then click Join. At this point, Linda is going to discuss our agenda.
Tonight, we have the welcome and introductions. Cassie's going to be talking about the design process, so the engineering design process. We're going to look at the STEM classroom and how we can use TI technology in that. And then we're going to look at several STEM activities, and those include a rotocopter with data collection using a motion detector, some data from the Center for Disease Control on concussions, and how we can use that data to maybe have students design a helmet. And then there'll be some discussion about free online resources.
Thanks, Linda. And Cassie is going to discuss our expected outcomes.
So tonight we plan to explore our new integrated science and technology, engineering, and math standards with TI technology. We also are planning to show you how to learn how TI-Nspire technology can be used in other ways for our data aggregation and analyzing data from the CDC. And then we're also going to look at how the engineering design process is applied to our new STEM workshop and how you can use the Nspire in a STEM classroom.
Thanks so much, Cassie. And Cassie, it's all yours.
All right. So I just want to welcome everybody tonight. And the first activity we're going to be looking at is the rotocopter activity in our STEM classroom. And we're also going to be looking at our new investigations and an emphasis on our new workshops that we're rolling out this summer. The new workshops have an emphasis on content with this technology as a support, and it's also based around classroom practices to enhance the student learning, and the new engineering design process that we are employing in our workshop. So the engineering design process is a process to help teachers and students to come up with new ideas and based around project-based learning. And our new workshop have this new model, and STEM in the classroom is a hot topic right now, and a lot of people are gravitating towards it, and the TI technology helps bring the STEM to life in the classroom. So this was the model that a few of us got together this past summer and put together to help teachers and students come up to a solution or project and creating things in the classroom and that have more than one answer. So Inspire STEM is our main goal here, and the first process is identify the problem. What's the challenge you're giving your students? And then, of course, they have to ask questions, research about the problem, and then they can design something, whether it be on paper, you know, on sticky notes, on a whiteboard, on their tablets, whatever means they need to go through to help design to meet the challenge. And then they can create that, whether it be build something physically or it be a process that they have to go through, and they can choose to evaluate it, how did it work, and then there's the communication step that's going back as a group, maybe coming to you as a teacher and presenting their ideas amongst the group and getting feedback, and they can either restart the process or go back to the design process. And this is what our new workshop is based around. All the activities go through this process where the students are guided through identifying the problem, going through some research questions, collecting data, analyzing it, meeting a goal, and determining whether they met the objective or not. So our first activity is the rotocopter activity, and I pulled up the teacher handout. So let me share my desktop here.
Hey, Cassie, while you're doing that, Mark had a question. Mark was wondering if the workshop that you just referenced, if that was for students or teachers.
It is for teachers. Can you still see my desktop? Yeah, there it is. Okay.
Yep.
You have to see my desktop now. All right. Okay, so this is a sample data collection from the rotocopter that we have. And so here's the activity. Basically, in the student activity, we give you this objective to design a rotocopter and use a motion sensor to calculate the terminal velocity. And there's a template for the rotocopter that students cut, and then they can adjust the weight, they can adjust the wings, cut the wings, they can even determine the type of paper that they want to use. And so the main idea is that they want to maximize the terminal velocity. So this is the teacher handout. It comes with the PDF in the document, and then a motion detector is what is used to collect the data. And then we gave them various tape, maybe some different types of tape, you know, whatever they wanted to pick. And then, of course, competition is always great in the classroom. So many prizes for the kids. And we have a video of this, so I'm actually going to share this over to Linda real quick. And she's going to show the video of us collecting the data. All right, let's do that again. It's so fast. So you can see that the rotocopter will fall towards the motion detector. It took us a couple tries because you're going to get some really interesting data, which is pretty cool. And the kids can determine how high they want to drop it. We're dropping it about 2 meters from the motion detector here. So pass it back over to me, and we'll look at the data. Okay.
There you go.
All right. Let me pull back up. Okay, so this is the data that we got when we dropped the motion detector. And it's this trend line right here that we are actually looking for. Oh, I guess it would be good if y'all can see my screen, huh? There you go. Can you see my screen now? Okay. So this is the trend line that we're looking for, is right here. So, and you get these weird little spikes here as the rotocopter is actually rotating the sound wave from the motion detector bounces back up to the ceiling. So we actually want to look at this trend line when we collect the data. And it took us a good 3 or 4 tries to get some really good data. And I'm going to actually go through here. I'm going to select some points. And what's nice on the Nspire is if you click and drag across, I can strike my data on the outside of that so that I just want to analyze that portion and not have to worry about what's going on outside of that trend. And in this lab, the kids can't run a regression because of the noise that we have with the motion detector. So it is meant to be a model function. And if you go to Menu, Analyze, we have a function for a model. And what's nice about this is the kids really have to think about their values of what they're going to pick. Is the graph linear? Is it exponential? And so it gives them in the mode of determining the values for the model itself. And we can see that the trend is actually linear, or we're going to test it as linear. And so here you can see that they actually have to determine the M value. And the spin increment is something that's set into the system to where I can change that M value. And if I change it, it'll go up by 0.1 each time. My B value being the y-intercept, and then the spin increment is how much I can change it by. And so I did some earlier numbers on this data, and I end up with -1. And I'm just going to say that my B value is approximately 1.5. And I'll show you how the spin increment works. It allows us to change those values. So you can see here this dark line ends up being our model. And if I look on my left-hand side of my menu, I see that this is my model function. And when you click on that, here are my M values. And so I can adjust the slope value or my B values. And when I click up, it goes up by 0.1, which is what my spin increment was. So I can adjust that model to fit my trend and my slope.
Hey, Cassie.
Yeah?
Renee had a quick question. She wanted to know if the rotocopter was calculating the velocity, or I guess if the CBR2 detector was calculating the velocity, or what's that actually measuring?
The motion detector measures the position versus time graph. So if you see here that I have a position versus time and a velocity, it will actually do both. And here is my position graph. So I'm going to zoom in on just my position graph.
Right. The velocity graph is so noisy that it's not a very good use. You know, you can't use that very well. And that's because as the rotocopter spinning, it's missing the rotocopter some of that time, which is why even the position graph looks noisy, but you can see the trend of how the position is changing with time, which is what Cassie's modeling.
So. Oh, well, all of a sudden it got real touchy. All right. So I can see that my terminal velocity is about 1.1, and it's pretty good, pretty linear. I mean, we do have a little bit of noise here because this is where the sound wave bounces back up. It goes actually through the blaze and bounces back. But we did, and then the kids would do how did they maximize that, the terminal velocity, so they want it to be slower. Or you could have them adjust it faster, who's going to fall the fastest or who's going to have the slowest, whichever way you want to go with it in your classroom. You can have them do both. And they can look at the rate of change or what factors are going to affect this rate of change. So with the velocity versus time graph. And it's a lot of fun. So
Cassie, one thing that I think is pretty slick, so you were just talking about like what's changing, but if we talk about one thing that's staying the same with that graph, one thing that looks pretty constant is where the CBR2 is actually missing the rotocopter. It's probably hitting, I'm guessing, probably your ceiling in your room.
Right.
And so I think that's awesome that that is consistent, as it should be, because hopefully your ceiling is not changing, or hopefully the position of the CBR2 isn't changing. But that, I think, is also a good discussion that you could easily have with your students, and they could try and figure out, well, why is it spiking like that? Like, what's it actually hitting off of?
Right. So in this lab, in one of our teacher workshops, in the STEM one, this comes from another STEM workshop, our investigations workshop. We do the parachute activity, where they have to design a parachute to drop the slowest and what goes into making the best parachute, and they collect the data similar to this. And it's not as noisy, but the rotocopter, they do get some interesting data, and it's a modeling function. So this activity brings in lots of different aspects, especially for, math classes in the modeling, having them thinking about what's actually incorporated into the slope. It takes some practice to make sure that your slope values are right. If I look at the difference of this point here, let's see, wait a minute, if I minimize this real quick. So it shows me here that it's at time 1.25 seconds at 1.015 meters. And then I can go down here, and they actually have to do that slope calculation. So to get that value, and then have to think about what their V value is going to be, and that the slope represents a change in position over time. So for that velocity. And then they, of course, redo the rotocopter to either add weights or take off weight, maybe change their paper. And then you would have them prove their second set of data, how did it change? So, and yes, since our rotocopter started way up high, our position is getting less and less and less, making a negative slope.
And then, Cassie, Carl Hines had a question. He just wanted to double check that you're having your students use the model function to calculate the velocity. Is that what you're doing?
Right. The model function, because we can't run a regression because of the noise. So we're having them run a model function to model this data, and then they can adjust it using their increments, the V values down here, to get the exact slope and y-intercept for that data.
And this is I'm going to add in here, this is a really good example of why you can't always just take data and run a regression, and that you have to have multiple ways of analyzing the data, because if you tried to run a regression here, it would take into account all of the data and not just the trend line that Cassie's modeling. So that's the whole value of having students be able to think about, when do I run a regression, when should I use a model, maybe I should do both, and compare those values. A couple more things, Cassie. I'm reading the chat, and so people were asking about the terminal velocity, and it reaches terminal velocity pretty quickly, and it's negative because the way we have it set up is it's falling towards the CBR, which was on the ground, and so we dropped it that way, and so as it's approaching the CBR, it's decreasing its distance from it, and so it's negative. So the velocity is negative.
And Amy had a question. Amy wanted to know, how long do you typically spend on this activity? So how long do you have for setup, students to utilize the equipment, et cetera? Like, how long does this activity really take you, Cassie?
It's a one-day activity. They can do it in one day for sure. It doesn't take them long to design the rotocopter to get it together. And then most of us teachers, if you've never done a modeling before, you may have to show them how to do a model in the Nspire. But this is an activity that is good to show them that, and then they can go and modify their design and come back and prove what they did with their new design for their terminal velocity, so to show that it went slower. So.
And you could, if you're short on time, you could have students collect it make one the first day, and then as a homework assignment, make a modification of it and bring it back the next day and just collect the data in class. So those are other ways that you can integrate this in without taking too much class time for the design part, where students have to go home and think about it and try it at home.
I like all the comments. The comments are good.
A couple things, yeah, right. If it's reached terminal velocity, it's no longer accelerating. So that's what that means, that basically the downward force and the upward force of the air resistance are balanced out. And so it's going at a constant velocity, and that's when terminal velocity occurs, is when the weight of the object and the upward air resistance are equal. And so at that point, it's got a negative velocity, but it does not have any acceleration, because it's actually going at a constant speed or constant velocity downward. A couple other things that I noticed just from the chat box.
Yeah, and so what Linda was talking about, like I pulled up on the teacher handout, we talk about in the student handout, there's the idea of forces and, what causes terminal velocity, that friction, the weight. So there are some guiding questions and some sample data, collecting that data, and for the teachers how to model the function, the instructions.
And some students get pretty good data, as you can see that Cassie's going through, without a lot of noise, but we wanted to show you that sometimes you can get that noise, which is what happened to us when we collected it just a couple days ago again, and that it's still a good activity, that you can still find the model, and it still works great.
So most of the time my labs have lots of noise, and so we always have to look for a trend. Hardly ever is it perfect. And then we also have some navigator tips in here, where if you have a navigator system, to use the navigator for students to show their data and explain their reasoning and to talk about it as a group, so to help with discussion.
And I would say that the navigator is a really great tool if each student goes and finds their trend line, and then you can just analyze each group really quickly with the navigator. It's very obvious which team wins the competition. If you're trying to have either the slowest terminal velocity, or as Cassie said, sometimes you could have the fastest, then I would say the slowest would be the biggest challenge, because that's what you want them to try to make it drop as slow as possible. Then you could have them basically put them all up and make a comparison, and it's pretty easy to see, for them all to see which one is the best based on the slope of the line.
But it's a good activity. Linda, are you ready for me to pass it over to you?
I am.
All right.
Okay, so one of the other activities, Cassie's passing it to me.
It's coming. Maybe.
Okay, I'm on the, here we go. Yeah, whoa. Okay, and I'm going to share my desktop with you. So one of the things we wanted to look at, hold on a second. Was, what else can we have students do, and how can we have them analyze data and use that to actually figure out why they'd want to design? And that's the whole part of, identifying the process and then doing some research. So one of the things that we came up with was looking at concussions and how many students now are getting a concussion, or I've had more students in my classes that have concussions than I can remember in many, many years. And Cassie and I both are at the same school, and so we were talking about this. So we decided to look at the CDC and get some data on concussions. And so this is one of the activities that actually has students first do some data analysis. And this is something where you could, if you really want to do some STEM, you could have some things happening in a math classroom and some things happening in a science or engineering classroom and be going back and forth. But this is the Center for Disease Control, and they collect data about traumatic brain injuries. And so the data in this table shows the rates of traumatic brain injuries related emergency visits by age group in the United States. And this was from 2001 to 2010. And that was per 100,000 U.S. population. So when you look at those numbers, that's per 100,000 U.S. population. So we took this data and we thought, well, what can we do with this? We can look at what's happening over the years, okay, what's happening to the data, and do we see a trend? I mean, you can see it in the data table, but you can also create an Nspire activity. So that's, the data is entered here. Okay, and what we did is years since 2000, so that when we went and the way that the data was set up on the CDC site was in groups of every 2 years. So basically when I put it in my document, I put it by 2, and then put the numbers that corresponded to this sheet. So 5 to 14-year-olds and then 15 to 24-year-olds. Okay. So here's the data, and then you can look at adding. So to do this next part, let me just go back a page, and I can basically go and add a page, and we added a data and statistics page. And then from there you can click, and I have both the graphs on the next page, but you just click on the axes and you can put years here, okay, and then you can put over here what you'd like to analyze. So this is the first set for the younger group, and then you can also change the axes for the older group. So either one, you can see that the number over those 10 years seems to be mostly increasing, okay, and just in 10 years. So then what students can do is they can analyze the data in a couple of different ways. So this is using data and statistics. So there's actually 2 different ways that we're looking at data analysis. The first one that Cassie showed you with the rotocopter was using the Vernier DataQuest, where we collected the data with a probe. In this activity, we're just analyzing the data, and there are 2 different ways that we can, well, there are actually 3 different ways here. When you look at analyze, I can add a movable line, I can plot a function, which is write my own function, or I can do a regression. So, and there are advantages to each one of these. So if I add a movable line, then I can, if I grab that line, and you grab it on your handheld by moving to the outside here, and I always hit, I hold down the click key until it grabs. On the computer, I have to just use my mouse, but I can adjust the slope out here. And if I move to the middle of the line, I can grab it and change the y-intercept. Now, if I'm working with Algebra 1 students, I really want them to be able to understand how do the slope and the y-intercept affect the line, and I like to be able to do that with real data so that they can actually relate it to something they understand and then interpret what does the slope mean. So if you think about the slope, it's the number of traumatic brain injuries, and that's per 100,000, and how that changes per year. But I can also, if I'm working with older students, So in my AP Physics class, I might have them either plot a function, which means I can write my own, or I can run a linear regression like this, and then I could compare how does the linear regression match up with the model that I came up with, and why might it be different, and why might sometimes mine be better, as the one that Cassie showed in the last activity where you had a lot of noise and a regression wouldn't be very good. Or if you have a point that you know you made a mistake in the lab or something really went wrong, then that might be another reason why your model might be better. So this allows us, the student, to look at how that's changing per year. And then we have another activity, and I'm going to go to my Nspire back, whoops, sorry about that, where we looked at categorical data. I'm going to go back to the beginning here. Okay, so this is analyzing concussion by age, sex, and sport. And there are a lot of middle schools who are really looking at categorical data as part of their curriculum. And so this next page shows the numbers of concussions as reported by emergency room visits by age and sport. And it only shows the top 5 for each sport and age group because it just got to be too many things. You could go to the CDC site and add more data if you wanted to, but I only chose the top 5. So here's what we have. We have the sports, football, bicycling, basketball, and there are others, and we'll look at some of these: skateboards, soccer, gymnastics, horseback riding, playgrounds, ATVs. And then up at the top here, these are the categories. So these are males between 10 and 14. These are males between 15 and 19. These are females between 10 and 14 and females between 15 and 19. And so then we might want to analyze this data in a variety of ways. Whoops. Okay, hang on a second here. And so I'm going to add a data and statistics page. So I just hit Control Page, and I think I've already added one over here. Okay, so I can click down here and add a variable. So maybe I add the sport. And so here are all the sports. Whoa, hold on. Here are all the sports that I have listed. And if I click over here, I can add a certain age group. But that's not really as meaningful. So I can go to the menu, and I can go to plot type. Hold on a second. I think I have to force the Y categorical first. So I'm going to force the Y categorical, click down here to add the sports. All right. Now I can add these. Nope. Okay. Menu, plot properties, plot type. All right. I'm going to start one more time. I think I messed up a little bit here. I'm going to add a page. Escape, escape. Add the page, data and statistics. Click down here, sport. Go to the menu. Add Y summary list. Now, there we go. So there's my bar chart. Sorry about that. I did talk you through it, and it is in the handout that Michael will post. So this is looking at, for females from 10 to 14. And as you move over each bar, you can see what percentage of concussions per 100,000. Okay, and here's other. So now if I look at females 15 to 19, you can see that that changes. Now, some of you might want to look at it in a bar chart, but you can also go to the menu, and under the plot type, you can change it to a pie chart, which is also nice. And as you hover over each individual section, you can see, and I think this one, I like looking at the pie chart a little bit better. So you can see for females age 15 to 19, soccer is 16%, basketball is 14%, gymnastics and cheerleading are 9%, horseback riding is in here, and baseball, softball. If I look at males in the same group, you can probably guess what the highest is if you think about it right now. Football, 30%. Bicycling, baseball, basketball, baseball, softball, ATV injuries, and then other. If you look at males in the same, at the younger age group, it's a little bit different. And so football is still the highest, but there's bicycling is pretty high and pretty close as opposed to what it is with older students. So it's pretty interesting to be able to look at this and then start thinking about, well, what if we wanted to help students not to get so many concussions? And we talk about helmets are required on bicycles, helmets are required in football. Maybe if we look at the females, we think, well, maybe helmets should be required for soccer because about 16% of the concussions for girls are in soccer, so maybe some kind of headgear would be good. We can actually have students then try to design a helmet that would help with all of these different kinds of things. And it may be that they want to look at the different kinds of sports and what kinds of injuries are occurring to determine what kind of helmet and how it should be designed, because one for soccer might be totally different than one for horseback riding or football or something else. So the next activity we had for them was to actually think about helmet design and try to come up with what's the physics behind all this. So helmets are important to reduce injuries during a collision. And so, of course, people would discuss with their group where people wear helmets for safety. And then we brought in a little bit of physics, talking about forces and why students get injuries. And so the brain is surrounded by the spinal fluid, and we talk about how Newton's first and second laws, the second law, F equals ma, causes a problem here. So if you discuss with your group how Newton's laws would show the motion of the brain, so basically if the motion is going, the first law says it just keeps on going in that same direction unless acted upon by an unbalanced force. So if you get hit, your brain keeps going and then it collides with your skull, and that's how a concussion can occur. And so it talks about acceleration, and so this could be the part that's maybe used in a science course, or it could be used in a math course where you say, think about what you've learned in science if they've studied this, and it has them do a little bit of algebra and talk about momentum, which is also the product of mass times velocity, and that's why things keep going, and impulse. So a big idea in helmet design and crash collisions and bumpers and all those things is impulse. And impulse is equal to the force times the time during which it acts. So if you think about when you watch a movie and you see people jumping out of a high building, and the way that they end up okay is that they land in something soft. And so what happens is they have to be slowed down from a certain speed with which they arrive at that object. But if you can extend the amount of time, so if we look at this, the force times the change in time, then that's what impulse is. So if you can extend the time, then the force is decreased. And so impulse is the force times the change in time. So whenever you design a bumper or a helmet or anything, what you want to be able to do is if an object's going to move and come to a stop, if you can extend the amount of time during which that happens, then the impact of the force is a lot smaller. And this is why another one that I have my students do all the time is I have them jump, have everybody stand up and jump. And what happens is when you jump and you land, you have to bend your knees. The reason you bend your knees is because then what's happening, your whole center of mass comes to rest over a greater period of time. If you jump and you land without bending your knees, you feel a jolt through your whole body. And that's what's happening if you have a crash without a helmet, is that you come to that sudden stop rather than slowly stopping like you do when you jump and bend your knees, which allows you to come to rest a lot slower. So that's an important idea in helmet design, is how this change in momentum occurs. And so we kind of have some questions. Okay, so now I passed up a little too fast. So the design project is, in this activity, to create a cushion to simulate the head protection using only the materials provided. And now what we did, and we had lots of discussions about ways to do this. We talked to Vernier, and there have been some people that are doing some other kinds of more complicated experiments. But what we did is, Cassie and I, is we just took and decided one that everybody could maybe do in their classroom is just drop a racquetball on the force sensor and then add some kind of padding or something to it and then drop it again and see how that changed the force. And part of this was we had lots of people using accelerometers, force sensors, and I went to some of the people in my math department and I said, well, would you do this and drill this and glue this all together to make this other thing? And the woman next door to me, she said no, and I said, would you drop a ball on a force sensor? And she said, I can do that. And I said, well, so that's kind of why we did this. We wanted something that everybody could go out and try to do, but you could certainly find some ways to enhance the activity if you want to. So what we did is we dropped the racquetball from 1 meter, or I think in the video that I'm going to show you, we did it from a 1/2 meter onto a bumper attached to the force sensor. So let me show you a couple things first of all. I'm going to play this from the beginning. Okay, so one is if you use a force sensor, and we tried to use something that was fairly common, you can take the hook off and you can put a little bumper on, okay? And so if you're going to do any kinds of collisions, and you could do this with designing bumpers. We have that in one of our STEM activities as well, where students take cars and design the best bumper. You can just take that off. The way that you collect the data, so if you're new to this, one is you can use the lab cradle, and this is the TI lab cradle, and you just plug the force sensor in to the side over here, and you slide the Nspire right in there, and then that acts as your interface. And the lab cradle allows you to collect, if you had multiple probes and wanted to do more complicated experiments, you could collect 3 analog and 2 digital. So you could use a motion detector along with the force sensor if you wanted to. And I just did an experiment in my class with that, actually a couple in the last few weeks, where I wanted to have them look at a collision and figure out the velocity as well as the force. And we just did one this week with a mass on a spring and put the motion detector and attached a force sensor so we could get both the force and the motion of the mass oscillating. But so if you want to use more than one probe, you have to use the lab cradle. If you want to use just one probe, so if you're just going to drop the ball onto the force sensor, then you can use the Vernier EasyLink shown on the right. And you just plug the force sensor in, and then you connect that to the Nspire, and you're ready to collect the data. Okay, so here's our video of us dropping. And so what we want to do, if you want good data, and I'm going to show you this, we're using the meter stick and we dropped from a 1/2 meter. And notice a couple other things before I play it again. I clamped down the force probe so that, I'm going to pause it here. Okay, so if you just look here, we clamped it down because you don't want the force probe to move because that's going to affect how accurately it takes the data. And we just basically dropped the ball onto the force sensor, and we're going to look at how much force there is. And then we're going to do the same thing with we wrapped it in bubble wrap, but you could have different kinds of supplies and have different groups try to do different things and see what happens to the force once you do that. So here's one more time. It's clamped, and then we're going to go ahead and drop the ball. Here we go. Okay. Here's our data. Hold on. Okay, so with no cushioning, this was our data, and it came down that the force sensor measured about -15 newtons, roughly, and we actually did several runs. So here's another run, and it's pretty consistent. And because the collision is over a really short time, you want to make sure that you do a couple of runs because it could be that the maximum force value actually occurred in between your timing. So we set the timing to be really short, as short as we could, take as many samples per second, and really collect it only over 2 seconds. And if you click on here, so all you have to do to trace on the data is click on it and then move your cursor around. And if you notice over on the left, it's showing the values for each time, okay? And so if I look, it looks like about negative, that's I guess about negative 13, so not quite down to negative 15. Okay, and this was with no cushioning, just like we showed you, just dropping the ball, and pretty consistent results. The second one was with cushioning, and we have several trials for this as well, I think. Maybe not.
Linda, click on the gray.
Oh, yeah, up here. There we go. I was like, oh, yeah, I clicked on the wrong thing. Right, okay, so we have several trials here. And so you might need to actually look at the greatest one or average them. I'm not sure why this one's a little bit greater. But if you click on these and trace across, hold on. Okay. Thanks, Cassie. You can look at the values, okay? And one of the things that you might want to do if you're teaching a calculus course or more of an advanced physics course, so this is an activity you could do with students different levels, and that was one of the things that we tried in our design is to find something that, you know, a middle school student could do this and just look at what's the force. A calculus student might want to do this, and I'm going to click off on this, and maybe I'll just look at this one. Okay, and maybe what I want to do in calculus class or in maybe an AP physics class is look at this data, and as Cassie showed before, you can select out a portion of the data and just look at that a little bit closer. So basically you just click and drag across, and then when you go to the menu under data, you can strike the data, and I want to strike the data outside that region. Okay, so I've gotten rid of everything else, and now I want to kind of expand this so I can see a little bit more clearly what's happening. So if I go to data, I can also, graph. I can auto scale, and it's going to expand that. Okay, so now I can see what's happening during that collision. And so basically I'm just using this part right here, and Sean just added a comment that you can use some triggering. So if you're more advanced, you can do that as well. From a calculus perspective, if I'm thinking about the force times the change in time, if that force is constant, I just can multiply that because I've got force as a function of time. But if the force is varying and I want to figure out what my impulse is, then I can go to Analyze and actually do an integral and find out what that region is right here. Okay, so it will actually calculate the area between the curve and the axis and give me a value. And what you hope to see is that when you look at this versus the one, and I know we probably don't have enough time to go into a lot of detail and show both of them, but if you look at how much time it took to slow down with the cushioning, this time width should be a little bit wider than it was when we didn't have any bubble wrap over it. And so this is an activity where students at middle school can just maybe look at how does the force change, but students at high school can look at in a little bit more detail and kind of see, oh, here's an application to something that I've learned in calculus and how it impacts what's happening in the collision. So that's kind of how we wrap this one up. I think, let's see if I have the other activity open, and I think I don't. So if I come back to this over here, helmet design. Yeah. Hold on. Okay.
Linda, there's a question on the picture of the racquetball with bubble wrap. No, we didn't end up taking a picture of it with the bubble wrap, but we did modify the racquetball itself. We did not modify the sensor. So
right.
Just some clarification there.
Right, and here's a little bit more. When you look in the activity, it does give a little bit more information about the data setup and how many samples per second you should take. And, a couple other things about using the force sensors, that before you do it, we zeroed it, and you can reverse the readings so that they could be positive rather than negative if you want to do that. And that's all in the menu when you're connected to the sensor. Other comments and questions? Okay. So this basically, when you go through this, it gives you all the information about analyzing the data that we just looked at. And so the impulse is the change in momentum, and basically that is the force times the change in time. Okay. I think that's about all on that activity. Cassie, do you want to add anything else? You've been probably monitoring the chat while I've been talking.
Yeah, I have. No, we've just about hit all the questions. There was a question over impulse and the graph, and we got that answered. This activity is new. It's up and coming, so if you joined tonight, this activity is actually in our newest workshop. And so, you know, you're getting a great preview of our new workshop tonight, and we hope to see you this summer.
And there are actually 2 STEM workshops that TI has now. So the rotocopter was from one of the workshops, and then this helmet design and the engineering design process has really been integrated into the other workshops. So we've tried to come up with 2 totally different workshops that don't have the same exact activity, so you have lots of options. So I'm going to stop sharing and turn it back over to Michael. And so I'm going to pass this to you, Michael.
Thanks, Linda. So as we begin to wrap up tonight, if you do have any last-minute questions for Linda or Cassie, please feel free to use that chat or Q&A window and get those questions asked. I would share a few resources that are available on our website, education.ti.com. And one of those, I think, Linda, you were just mentioning the T-Cube summer workshops. And so you can find more information about that at the bottom of our website. And this summer we have over 70 workshops available across the United States and Canada that focus on things like STEM or possibly certain types of technology. So if you're really looking to learn more about TI-Nspire technology, or maybe look at the new TI-84 CE, different types of technology, pedagogy, and content are all available with different workshops across the United States and Canada this summer. Registration is open, so please feel free to visit this page and register for any workshop that you feel may apply to you. For the remainder of the spring series, we're going to be giving away to one lucky attendee free registration for a summer workshop. And this week's winner is Levia Hopsteller. So Levia, we will be contacting you in the next couple of days with more information.
That's pretty cool.
Yeah.
Yay.
So congratulations, Levia.
I'll just add in, we have hosted several years at our school, and a lot of our teachers come, both math and science, and it's been a great experience when we can get our math and science teachers together. I'm both math and science. Cassie is trained in math and science, but teaching just science. But when we can get our math and science department together, working on how to help students, it's really a great experience. So.
Yeah, I think for me personally, I've attended and also instructed a few summer workshops in my day. One of my favorite things about them is just having the time to actually really get involved with whether it's technology or content or pedagogy, but you actually have the time to learn something, ask questions, and it's not just something that you just rush through and then all of a sudden you don't see it for another year. So I love the fact that all the workshops are given due time to sit there and really learn whatever it is that the objectives are.
Can I add one more thing that I saw in the chat window, Michael?
Yeah, absolutely.
Somebody was asking about force sensors, and so for some of these activities, like even with the force sensor or the rotocopter, if you don't have a lot of sensors, if you look at basically the force sensor, you just dropped a ball onto it. So even if you only started out with one, this is an activity that you could do because the data collection time is so short that when I didn't have very many, I would just have students come over and plug their Nspire in, set it up, collect the data, or I could, collect it all on mine and just send it to each group and let them go back and analyze their data. So you don't have to have a lot to actually get started.
Thanks. I also want to point out on our website, also under that professional development tab, you can learn more about PD in your area, which is another way to get to the T-Cube summer workshops. So I'm going to point you to the online learning. And if you want to possibly register for some upcoming webinars that we have, we do have a few more webinars that are available this spring. So please feel free to look over any of those that may be of interest to you. I know that tonight, briefly, we just mentioned the TI-Nspire Navigator system near the beginning of our webinar. And next week, we have a webinar that is focused on just that TI-Nspire Navigator system and how you do data analysis in chemistry, biology, and physics. So that may be right up your alley for a lot of people that are attending tonight. Please feel free to continue the conversation if you got excited about something that you learned tonight, or you have questions about things you learned tonight. Please feel free to use any of our social media outlets and either start a conversation or continue one. To receive a certificate of attendance, go ahead and click the link in the chat window. And that's coming right now. That link contains the name of tonight's event. Also listed there is a link for the documents that Cassie and Linda used tonight. So if you want to check out some of those documents and use some of those in your classroom, or maybe go through them on your own time with the recording and download those activities, that'd be a great way to use those activities as well. In case you miss a link to the certificate or the documents, you should automatically get a follow-up email within a couple days that will have links with the certificate, the documents, and also the recording of tonight's webinar. So please be on the lookout for that. Also, whenever you leave the webinar, a brief survey will automatically appear in your browser. Your feedback guides us as we plan future online events, and we really do appreciate your thoughts. So if there's any skills or resources you'd like us to cover in a future webinar, please let us know. We definitely listen to your feedback, and we really hope you share your thoughts in the post-webinar survey. So thank you so much, Linda and Cassie. I saw a few people that were mentioning that they appreciated the webinar, so I'm not the only one that thought things went well. So thank you so much for all the time that you put in getting prepared for tonight.
Thanks. It's been fun.
Thanks, guys.
We hope to see you all at some. Oh, I was going to say we hope to see you all at some future T-Cubed event.
Absolutely. I hope to see everyone back online next week. Thanks so much.